Don't miss out on our new videos by subscribing LogicHeap and pressing the bell icon.
Hello friends, welcome to LogicHeap. In this tutorial, we are going to study a second method of collision handling, which is open addressing method. In the last class, if you remember, we studied about separate chain method. That was the first method for collision handling. What we were doing there, in hash table, at each place we were maintaining a list to hold all the key value pairs mapping to the same hash value. Okay, so that was the separate chain method, but what was the problem with that method? Suppose for 3 we had 2 data, 10 logic. So we have the hash function as key modulo 7. 10 modulo 7 is going to give you 3. So at index 3 you need to keep this key value pair. So what you were doing, here you were maintaining a list with the key and the value. Next comes is 17 heap. Okay, so in the list you were appending this new data as well, 17 heap. But you see one thing here, we have empty space here as well. We have empty slots here in this table as well. Despite of that, we are using this extra space. So here we are wasting memory. That's why now we'll study about open addressing, where we use these empty slots available instead of creating another list to maintain it. So we'll be using this hash table only. This is called open addressing, when you are using the empty slots of your hash table only instead of creating some other auxiliary space. Now you are clear with open addressing. What is it? When you are using the empty slots of your hash table itself. Next is, there are different types of open addressing, because the slots you choose, the way in which you choose the slots, that makes different types of open addressing. The first one that we are going to study next is linear probing. Okay, probe, you know, probe means check. Okay, when you are checking linearly, one after the other you are checking in your hash table, this is linear probing. What I mean to say is, see, let's name this hash table as A. So this is A0, A1, A2, right? And now you know we are not going to create extra space. So firstly, you will put 13 ls when the data comes, 13 ls, where you will put it at 6, 13 modulo 7. The first thing that you always do is A of H key. So what I am doing in this hash table, which I am naming as A, in it add index H key. So how do you calculate H key? Key is 13. So A H 13, which is going to give you 13 modulo 7, which is 6. So at A6 you go and you will put this value. What is it? 13 ls. Right? Next is 10 logic. So again you will go at AH key this time is 10. Okay. So it is going to give me what? 10 modulo 7 A3. So you go at A3 and here you put key value pair 10 logic. Now comes a 17 heap. There's a collision, right? Because AH17, how much is it? A3. 17 modulo 7, it is going to give you 3. So at A3 you'll go, but this place is already occupied. In linear probing, you go to the next index, just next. So what I mean to say is, if this is evaluating to A3, you'll go to A3 plus 1. If this is also filled, you'll go to A3 plus 2. Okay, and every time if this value is increasing, we should limit it. We should put mod n here. Okay, so the logic here becomes is, you will start with A H key, okay, whatever it is going to give you, the index, plus I mod n, where n here is 7, the capacity of your hash table. So this is the approach you will be probing your hash table. And I will be, it will start from 0, 1, 2, 3 until you find an empty slot. Okay, let's revise what we did here. Firstly, as soon as any key value you get, any data you get, firstly you apply hash function to its key. So 10 modulo 7 gave you 3. So A3 plus I initially is 0, A3 mod n mod 7. So 3 mod 7 is going to give you 3, A3, you will go at A3 and you will place it. Then comes a 17 heap. So 17 modulo 7, it is going to give you again 3. So A3 plus 0, initially you will start always with 0. So A3 mod 7, which is A3. So at A3, you will go, but this place is occupied. Now what will you do? You will increase the value of I. I now becomes 1. So A3 plus 1, which is 4. A4 mod 7, it is going to give you 4. So you will come here and you will put heap here. Okay. Now suppose next data that comes to you is how much? Let's say 24 bob. Okay. Now 24 mod 7, it is going to give you 3. A3 plus 0 mod n, which is A3 occupied. You will increase the value of I. Now I becomes 1. Okay. So this becomes A4. You will go at A4. Again this is occupied. So you will again increase the value of I. Now I becomes 2. So A5. And this is empty slot. So you will put 24 bob here. Okay, so that's how you can do linear probe. We just saw how we can do insertion in hash table in case when we are using linear probing. Now let's see how we can do search in it. Suppose you have given a key as 24 and you need to search its value. Now what will you do? First thing what we always do is we use the hash function here. So 24 modulo 7, it is going to give you 3. Now you will go at index 3 and here you will check the key, it is 10, it is not equals to 24. So using the linear probing formula, now we will go to the next index. So I currently was 0, now you make I as 1. So you will go at A4 and there you check if 24 and 17 are equal. No. Again you will increment the I. Now I becomes 2. Both the keys are matching. So here you will return the value Bob. So you do this search until either you find the value, key value pair, or you find an empty slot. So after empty slot you will not be having the keys which are mapping to this hash, right? Give it a thought. So that's why we do the search till you find an empty slot. So this is how we do insertion and how we do the search. Now there is one problem here. If you are using the linear probing, it is going to create some sort of clusters. If there are values which are hashing to the same index, it is going to create a cluster. All these values are at one place and this all is empty. This type of clustering, having all the values together, key value pairs at one place in the hash table, concentrated at one place, this is called primary clustering. Okay. So in linear probing, the problem is this clustering of values, while this is completely empty and this place is occupied. So the problem with this is when you are going to do the search, this search is going to be longer. Okay. So as the concentration increases, as the clustering increases, your search becomes slow because you are looking at so many values. So that's the problem with linear probing, primary clustering. Now let's talk about different type of probing, which is quadratic probing. So now let's see quadratic probing. This very minor difference, what is it? Here you have I, change it to I square. Okay, so the way you are probing now changes. Firstly, I is 0, so it's 0, you look at the place. Then I becomes 1, so you look at this place, suppose. Then I is 2, so 2 square, which is 4. So 1, 0, 1, 4, 9. That is how you are progressing. Okay, so it will help you in not getting the cluster at one place. This is the benefit of using quadratic probing. So let's see how it will work here. Let's start with 13 LS. 13 modulo 7 is going to give you 6. So you'll put this key value pair here. Then you have 10 logic. So 10 modulo 7 is 3. You'll put it here. 10 logic. Then comes as 17 heap. So 17 modulo 7 is 3. You will come here. This is already occupied. Now you will increase the value of I from 0 to 1. So a H key, which is 3, 3 plus 1. Okay, it is going to give you 4. 4 modulo 7 is 4. So you will put 17 heap here since it is empty. Now the next is 24 bob. So 24 modulo 7 is 3. Now you will come here. Initially the value of I is 0. So A3 mod 7. So A3 occupied. I now is 1. So A4, it is also occupied. Next I becomes 2. So 2 square is 4. A3 plus 4 mod 7. Okay. 7 mod 7, it is going to give you 0. So at A0 you will put 24 bob. So that's the benefit of quadratic probing, that all these values are not getting clustered at one place. Now you got it how we can insert the values. If suppose you want to search the values, how will you do this? Using the same method, a H key plus I square mod n. So initially I will be 0 when you will start the search. Suppose again you need to search for 24 bob. So 24 modulo 7 is 3. A3 plus 0 mod n. I initially is 0. So you will search at A3. Then you will increase the I as 1. So A3 plus 1 mod n. At A4 you will search, it is again not equal. Then you will increase I to 2. So A3 plus 2 square is 4. 7 mod 7. At A0 you will look for the value. Yes, it is present. So you will return bob here. So that's how you can do insertion and search in case of quadratic probing. You understood primary clustering in the case of linear probing. Here all the values were concentrated at one place. Now in the case of quadratic probing, for sure you will not get primary clustering. But see, if the values are hashing to the same index, all the keys are hashing to the same index, for all those keys you will be having the same sequence generating formula. Okay. So in that case also it is going to give longer check for finding your key value pair. So you will not say that values are concentrated, but somehow you are using the same generation formula for insertion and searching, which could lead to longer probes, right? So such type of clustering is called secondary clustering, because you are using the same generation formula, it will lead to longer probes. So that is called secondary clustering, where you don't see the clustering but it is present there. It is better than primary clustering, but it is very much present here. Now we learned two types of methods, linear probing, quadratic probing. Let's learn double hashing. Now we are going to learn another type of open addressing method, which is called double hashing. It is considered better than linear probing and quadratic probing. So in double hashing, what you do is, earlier this was the formula that we were using for the linear probing and this for the quadratic probing, right? So this slight change in it, a H key okay, plus I, so that was what we were doing in linear probing. Now I gets multiplied by another hash function. So that's why the term double hashing. And this whole mod n. Now here see this thing, we are not going to make it 0 at any point. So I starts from 1. Okay, 1, 2, 3, 4 up till you don't find an empty slot. So this is the double hashing. Now why we are using another hash function? Because we want to randomize this thing. We saw earlier that in the case of quadratic probing, though there was no primary clustering, but the same sequence was generating for all the values which are mapping to the same index. So there was not primary clustering, but there was secondary clustering. Now we want to make it more randomized. So that's why here, just instead of taking just the I, we multiplied it with another hash function. And this hash function is generally like R minus key mod R, where R is less than your table size. Generally it is like that. So why we are taking it like this? This is beyond the scope of this tutorial, but you can learn more about it. One more thing, R and N, we generally take it as prime. Okay. So this is your double hashing, where you are using one more hash function and you multiply it with I. And you take such hash function which doesn't become 0 at any point. So you don't want this value to become 0 by I or by the hash function. So that's why you are choosing such type of secondary hash function. Cool. So let's try to use this hash function for this key value pair. Secondary hash function I'm going to take is 3 minus key mod 3. So let's calculate it firstly for 13 LS. So A 13 modulo 7 going to give you 6 plus, next thing is I initially is 1. Now S key, so 3 minus 13 modulo 3. 13 modulo 3 is going to give you 1. So 3 minus 1 is 2. Okay. And mod n, which is mod 7. So how much it would be? A 8 mod 7 means A1. So at A1 you are going to put 13 LS. Okay. Next is 10 logic. So here what will you do? A 10 modulo 7 is 3. Let's start it with 1. Okay. And then 3 minus 10 modulo 3. So 10 modulo 3 is 1. 3 minus 1 is 2. And mod 7. Okay. So 3 plus 2 is 5. 5 mod 7 is going to give you 5 again. So at A5 you will store 10 logic. You're getting this? So we'll change I every time if we don't find an empty slot at that position. Currently we didn't encounter any such value. Now 17 heap. So for 17 heap, A 17 modulo 7 going to give you 3 plus I initially, let's start from 1. Now 3 minus 17 mod 3. So 17 mod 3 is going to give you 2. So 3 minus 2 is 1. So it is going to give you 1 mod 7. So A3 plus 1, 4. This is going to give you A4. At A4 you will put 17 heap. I have actually changed this class for you to make you understand how it is handling collisions. So 33 John. So in the case of this last key value pair, 33 modulo 7, it is going to give you 5, right? Plus I is 1 initially. 3 minus 33 modulo 3. So 3 minus 0. So 5 plus 3, 8 mod 7, right? So this is going to give you A1. Now A1 is already occupied. So what will you do? You will increase the value of I. Okay. So 5 plus 6. 2 into 3 is 6. So 5 plus 6 is 11. 11 mod 7 is 4. Now this place is also occupied. So you will change it to 3. 5 plus 9. Okay, which is going to give you 14. 14 modulo 7 is 0. So here you will put 33 and John. Okay, so that's how collision we handle in double hashing. Now, all the things that we discussed in last class about the load factor. So, here also in the implementation, we'll keep load factor as 0.5. So, if the data becomes half of the size of your table, we increase or double the capacity of a hash table. So, this is the thing that concept we will use here as well. So here I am not going to make a tutorial on its implementation in Python because we have done a detailed tutorial of implementation in case of separate chain method. Though I am going to provide you code on my GitHub link, you can check it in description box.